Okay, covalent bonds. So again, we have two different kinds of bonding. Ionic bonding, we've got those electrostatic forces that hold our cations and anions together. And covalent bonding, we are sharing electrons, typically between nonmetals. Now, covalent bonding, we say, is an idealized type, because what the model here is that if atom A and atom B share electrons together, then atom A takes all those shared electrons and counts them as belonging to atom A, and atom B takes all those shared electrons and counts them as belonging to atom B, okay? Now, what we look at is the reason why this is most common between two nonmetals is nonmetals have much more similar abilities to attract electrons to themselves. When we have a metal and a nonmetal, the metal has a much easier time getting rid of electrons, whereas the nonmetal attracts the electrons. Okay? So when we look at our covalently bonded compounds, we have bonding pairs and we have lone pairs. Bonding pairs are going to be the electrons that are involved in bonding, and our lone pairs are going to be the electrons that are still around an atom but are not involved in bonding. Okay, so if I look at hydrogen, each hydrogen has one valence electron, all right? And so one valence electron, they pair up and we get a single bond. So a single line here, this is a single bond. And there are two electrons contained in that single bond, okay? So each hydrogen needs a duet. So if I have two electrons in that single bond, then this hydrogen says, cool, I'm good. I've got two electrons there. This hydrogen says, cool, I'm good. I've got two electrons there, okay? So each hydrogen counts those electrons as belonging to it. If I look at chlorine, chlorine's very similar, all right, except chlorine has more valence electrons than hydrogen, all right? So each chlorine has one unpaired electron. So that one unpaired electron needs to pair up, all right? So we pair up that unpaired electron on each one right here, all right? We get that overlap and we get our chlorine molecule, okay? And so we get an overlapping of those orbitals there, and now each chlorine thinks it has a full octet. Now, sometimes we need more than a single bond, all right? So we have lots of compounds that will give us single bonds, or lots of elements that will give us single bonds. So again, hydrogen and hydrogen gave us a single bond. If I bond hydrogen and fluorine together, I get something that looks like this, okay? So a single bond. All right, so I have 6 electrons around fluorine, 3 lone pairs. Still need 2, 6 plus 2 from that bond gives me that total of 8, and then hydrogen needs its duet. So there's the 8 for hydrogen, or the 2 for hydrogen. Okay, fluorine is like chlorine. If I have those 2 fluorines together, right? So I've got 3 lone pairs around each fluorine, so 6 electrons, and then each fluorine decides that both the electrons in that bond belong to it, so they each have 8, right? Sometimes we end up with what we call double bonds. We get 2 lines there, and sometimes we get triple bonds. Okay, so we have 4 shared electrons in a double bond and 6 shared electrons in a triple bond. So oxygen, okay, does this, and so we have 2 pairs of electrons that pair up, so we get that double bond there. Okay, and so each line represents 2 electrons. And so in a double bond, we have 2 lines, we have 4 electrons. And so this oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. We are good for that octet. Okay, and so we get that overlap there, we get that octet. All right, we can look at our nitrogen. This is a triple bond. So a total of 6 electrons. And again, this nitrogen says all the electrons belong to it. This nitrogen says all the electrons belong to it. And so if I have 2, 4, 6 in my bonds, and then another lone pair there, there's 8, 2, 4, 6, and 8. Okay? So we satisfy the octet. Now when we look at covalent bonds, okay, some of the properties there, they're strong and localized. So they're held together there, so they're localized in between those two atoms. We get these cool things sometimes called network covalent solids, where instead of having a whole bunch of individual molecules, we have this vast array of everything that is bonded together in a full three-dimensional array. Diamond is like this. That's part of why diamond is so strong, is because it is a network covalent solid where everything is bonded together in that three-dimensional array. Okay, and our covalent compounds, they don't conduct electricity. There's no ions there. Okay, so we don't have an ion, therefore we have no mobile charge, and so we do not conduct electricity. That's why pure deionized water doesn't conduct, because just H2O, there we go, covalent compound, no ions. Table sugar, it's all bonded covalently. It still dissolves in water, but it doesn't form any ions. So if we test it with a conductivity apparatus, we don't see any conductivity there. And then our sodium chloride, though, that's ionic, so we have mobile charge. That's where we get the light bulb lighting up, and we do get that conductivity.